and welcome back to Maths with Mitch for another exciting episode. If you've watched my previous videos, thanks for joining me for another. If this is your first, then I hope you enjoy it and you watch some more. Today we're going to be looking at an introduction to trigonometry. So in today's lesson we're going to look at what is trig, what does the word even mean, and what does it apply to in terms of geometry. Why is it useful? So where are we going to use this in future life? We're then going to introduce you to the trig ratios and the basic trig ratios, and then we're going to use those to solve some trig problems. So without further ado, let's move on to what is trigonometry. Trigonometry is the branch of mathematics that explains the relationship between the angles and the lengths of the sides in a right angled triangle. So if we were to draw a right angled triangle as so, remembering that the symbol denoting that there is a right angle being 90 degrees, is given by this this small box in one of the corners, so that means right angle 90 degrees. Then trigonometry explains the relationship between a given angle, so we're going to call it theta. It could be called anything in your textbooks, doesn't matter which symbol people are using, how they're talking about the angle, but they're referring to a specific angle in the triangle, and then how it relates to the sides of the triangle. And specifically in trigonometry, we're going to call them, we're going to refer to them considered against this angle. So this angle here, if we were to just label up the points of the triangle, that might make it easier. And then we can talk about them in these terms. So we might refer to this angle as angle theta, but also you might see it written as angle ABC. And that means that from here, you're looking at A, B, C. So it's the angle that makes up between these points. So you might see it written angle A, B, C also. In terms of the other terminology then, they relate to the angle theta that you're looking at. So the long side of the triangle is always referred to as the hypotenuse. So you can remember that as the longest side, or you can think of it as the side that's going to be opposite your right angle. It's going to be directly opposite your right angle. And then the other two are in relation to the angle theta, which you're talking about. So when we said angle ABC, it's made up of these two lines here. It's made up of the hypotenuse and another line. That is the one that is adjacent. Adjacent meaning next to. So it's either next to the angle, or you can think about it as the other line that makes up the angle. And then the last remaining side is if you look from the angle you're looking at directly across the triangle, you then get to the opposite. So that's the notation we're going to use for trig, and trigonometry itself is going to explain the relationships between the lengths of these sides and the angle within the triangle. Just remembering, as I say, it depends on which angle you're talking about as to how you label it up. So if you were to draw the same triangle, again, right angled, let's refer to those as ABC, but we were talking in relation to this angle, again, we're going to call it theta. So the long side, as we said, the long side is always the hypotenuse. And then the other two are named in relation to the angle you're looking at. So again, we said for the rule, the hypotenuse makes up this angle with the adjacent, or it's the line that is next to the angle you're looking at. And then directly across the triangle from the angle you're talking about is the opposite. So the notation, it's always the same labeling, but it depends on which angle you're looking at as to whether it's the adjacent or opposite. So remember the rules. Hypotenuse, the long side, adjacent is next to or makes up the angle which you're looking at, and then opposite is the line which is directly across or directly opposite the angle that you're looking at and the angle of concern with your problem. So we're going to use trigonometry to define some of the relationships between these angles and the lengths. And what that's going to allow us to do is to have some of the information about the triangle and then find out some of the other information. So we might know the length of the hypotenuse, we might know the angle, and then we'd be able to find out the length of the opposite and adjacent sides, for example. Or it could be any combination of those things. And first I want to talk about is why is that going to be useful for you in the rest of your lives? Because I remember when I used to first do maths and the teacher was speaking out the front and they would talk about trigonometry and talk about ratios, and I would think, where is that going to be useful for me? And I couldn't quite see it. So I want to try and talk to you about a couple of examples of where it might be useful in future. So the first thing I want to really talk about is we're going to start with applying it to a triangle where you might know the hypotenuse and you can then find out the lengths of the opposites and adjacent sides. But I want you to understand that in future we're going to apply that in much more cases beyond a basic geometric triangle, and we're going to apply it to vectors, and that might then represent different things. So it might represent a velocity, it might represent a force. So you can start to think about how trigonometry might be used in circumstances such as when you get into looking at engineering problems and mechanics. You might consider anything going up a hill. It could be a particular vehicle, and you could have a hill which is at angle theta. You might be looking at a bicycle. This is a terrible bike, but let's say a bike looks like that. Now I'm going to keep it simple because we're just talking conceptualizing things, but you're going to be riding on the bike and you're going to be applying a force in that direction. That force is going to be at force theta. Now there's going to be obviously other forces acting on the bike, but what you can do with trigonometry, and which is going to be fundamental in future, is if you know the force that's applying like that, it's acting at an angle. But really when we're looking at how we're going to resolve the forces and think about how they're acting together and be able to add and subtract the forces and see how they're acting all together on one body, you want to split it up into the vertical and horizontal forces. So with trigonometry, you start to develop the mathematics that's going to allow you to split things up into a y direction and an x direction. And you can do that with a whole host of different things. And when you can do the basic trigonometry, that releases a whole host of potential of what you can do. So I'm talking about forces acting on a bike here, but you can start to see everywhere else that you can apply this. So you could apply it to a moving body such as a bike, or you can apply it to a static structure. If you were to look at the triangles in a bridge, for example, in a building structure, you can apply it to projectiles and how they're moving through the sky and the velocity that they're traveling with. Or let's think about you're now a ship captain, and you're going to be looking at how you're going to navigate your ship. Now you might want to get from point A to point B. Let's say you're traveling from point A to point B. Now if anyone's ever sailed, you'll see on navigation charts that you'll have currents that are acting, and they're essentially vectors that they and so you might see a current like this. This represents that the body of water is pushing in that direction. Now if you want to get from A to B and you were to drive directly for B, that current would push you and you'd end up over here. It would be pushing you in that direction. So therefore you can look at it and think, if I want to end up directly at B, I'm actually going to have to steer into the direction of the flow. That'll push me along this way, and that'll give the resultant travel directly across to B. So what you can do there then, if you know what that is pushing you at, then you can start to look at which angle and which bearing you actually have to drive at, and what speed, let's say speed z, you have to drive at to actually get to this resultant point from A to B. So trigonometry is going to release the potential for so many situations that you can analyze and actually apply the mathematics to explain what's happening in the physical world, and also to develop solutions and designs for things that you're going to actually want to make. So given that you're now armed with the desire for learning trigonometry, a bit beyond just having to learn it to pass a test, let's go into the trig ratios and look at it from basics with triangles, and then we'll develop the knowledge from there. So if we go back to looking at a right angle triangle, if I can get my pen to work. It's going a bit haywire here. Okay. Oh, I want a line. Okay, so getting back to our right angle triangle. And I want you to just cast your minds back to what we said at the start when we were talking about what trigonometry was, and we were talking about the notation. So we have the angle that we're looking at. So we're going to do some consistency and remain calling that theta. We are going to label up the hypotenuse, the adjacent, remembering that it is next to the angle of interest or makes up the angle of interest with the hypotenuse, and then the opposite, which is directly across from the angle that we're looking at. So first up, we're going to talk about ratios. So the trigonometric ratios. Now when we say ratios, that immediately springs to mind of a comparison of two kinds. So a ratio is looking at one thing compared to another. So I'm just going to tell you what they are, and then we're going to talk a little bit about what that actually means in terms of a ratio, before in future lessons we're going to get on to visualizing them in a unit circle and how we look beyond the basic triangle. So first is sine. So sine theta equals opposite over hypotenuse. We have cos or cosine equals adjacent over hypotenuse, and the final is tan or tangent. Tan of theta is opposite over adjacent. Okay, now you will have to put that to memory. So some ways that you can remember that is SOHCAHTOA, and that is a favorite by many. Now some people like to immediately write this at the top of an exam paper, for example. When you sit down, you're not going to forget it. It takes away one thing that you need to remember. But what you're seeing here with SOHCAHTOA is S stands for sine, the O is opposite, and the H is hypotenuse. So sine equals opposite over hypotenuse. And you can represent that if you want, thinking about it in your triangle. Sine equals opposite over hypotenuse. And the same then follows for cosine and tan. So you can remember this, you can remember it in triangles, but sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tan equals opposite over adjacent. So they're the ratios we're going to use. Now, I said at the start there, ratios, it's a comparison. So what are we seeing here? So if we just look at the first one here, sine of the angle. Now when we say sine of the angle like that, we're not saying sine times theta, which you can sometimes write algebraically. You might see two terms next to each other and you think they're times to each other. No, what we're saying is it's a function with theta as an input. So we're not saying sine times theta, we're saying what is the value of sine at this angle theta. So as this angle changes, the value of sine will change. And it will be equal to opposite over adjacent. So it's the ratio of the sine of opposite here compared to hypotenuse. So what we're saying there is the ratio of the length of this side, the vertical side in this case, compared to this length here, the hypotenuse. So it's a ratio of the hypotenuse, the opposite of the hypotenuse. And the hypotenuse, by definition, is the longest side of the triangle. And for a right angle triangle, the hypotenuse is always the longest side of the triangle. So that value is always going to be opposite is less than hypotenuse, so it's always going to be less than 1. So sine of the angle is the ratio of opposite over hypotenuse. So it's a ratio in the vertical direction compared to the length in the length of the hypotenuse. And we'll talk on the unit circle in later episodes. We'll talk on the unit circle, but you can visualize that. You can visualize how that changes across the angle and how that works around a full 360 degrees. But for now, think of it as it's the ratio of the length of the opposite side compared to the hypotenuse. Now, cosine, again, is the ratio, this time of the adjacent compared to the hypotenuse. But the same rule will apply. So it's talking about the ratio of this length here compared to the hypotenuse. But again, that adjacent is going to be less than the hypotenuse. For a right angle triangle, it's going to be less than 1. So cosine of an angle is the ratio of the length of the adjacent side compared to the length of the hypotenuse. And then for tan is a bit different. It's not got the hypotenuse in. It's the ratio of opposite over adjacent, but it's actually the ratio of sine theta over cos theta. But we know here, if we were to put these in for these terms, you've then got opposite over hypotenuse divided by adjacent over hypotenuse. The hypotenuse will cancel, and that leaves us with opposite over adjacent, and that's where that ratio comes from. But again, it's a ratio. It's a ratio of the length of the opposite side compared to the length of the adjacent side. So again, that's the building blocks of this are the geometry of a triangle, and it's all ratios in comparison of the different lengths of the triangle compared to one another, and how that relates directly with the angle in the triangle. So the next thing I want to look at is some common and special triangles that we might look at with trigonometry. Now, you'll have all seen your scientific calculator and seen the tan, cos and sine buttons on it, and before you dive into the calculator, I'm going to do all the problems using the calculator. I want to try and describe a few triangles where you can do without a calculator and you can visualize the process a bit easier. So firstly, let's look at a triangle like this. So as we said, it's a right angled triangle, and this triangle is going to be a 45 degrees triangle. Now we've got a right angle here, 90 degrees, we've got 45 degrees in this side, so remembering that all the angles in a triangle add up to 180, that would mean that this one is also 45 degrees. We're going to make each side length 1, and then we can use Pythagoras to find out what the length of the hypotenuse is. Remembering that Pythagoras, a squared plus b squared equals c squared, or you might have different variations but say the same thing. We can call this a, this b, and this will be c. So we have 1 squared plus 1 squared equals c squared. 1 squared is 1, so we have 1 plus 1, which is 2, equals c squared. So that would mean c equals square root of 2. So we can say that that side is the square root of 2. So given that we've just talked about SOHCAHTOA, let's write that out again as a reminder. We've just talked about trigonometry. We can apply these trigonometric ratios to this triangle and actually find out what sine, cos and tan values are for this triangle. So we said sine, and in this case we're going to look at this angle, it's theta, but actually you'll realize that they're both 45, so you would expect to have the same values regardless of which you're looking at. So we can say sine at 45 degrees is equal to sine is opposite over hypotenuse. So opposite in this case, if we look directly across from the angle, is 1. And then we're going to divide it by the hypotenuse, which we've just found out as root 2. So we know sine 45 is 1 over root 2. So already for that triangle, we've found a value for sine 45 degrees without even having to reach for the calculator. So that is a numerical value that you can now use. What about cosine then? So if we do cos 45 is adjacent over hypotenuse, we said, and we can see that here, adjacent and hypotenuse. So adjacent again is 1, and the hypotenuse is root 2. So we're saying the value for sine 45 and the value for cos 45, they're the same, 1 over root 2. Now, just looking at the triangle, does that make sense? Because what we're saying there is cos 45 and sine 45, remembering that they're the ratio sine for the opposite compared to the hypotenuse, and cos for the adjacent compared to the hypotenuse. So would it make sense for that ratio to be the same? And if you look at the triangle, the answer is yes. This is the adjacent, this is the opposite. They're both the same length, they're both 1. Therefore, the ratio of those compared to the hypotenuse should be the same. So visually, we can look and see some of these numbers are what we expect them to be. And let's now finish it off with tan. Now we've just said they're both the same thing. Sine and cosine of the angle at 45 degrees are both the same. And we said tan, let's see, tan 45, tan is the ratio of sine over cos. So when we do opposite over adjacent, which we're going to use based on SOHCAHTOA, that gives us 1 over 1. Therefore, tan 45 is 1. And again, look at it and think, is that what I expect? It's the ratio of the sine of 45 over cos 45. We know they're both the same value, therefore yes, I expect tan 45 and the ratio between the two to be 1. So that's a special triangle, a 45-degree triangle. Now let's look at a half equilateral triangle. So remembering the word equilateral means that all the angles and all the side lengths are the same in the triangle. Now immediately we're thinking that that doesn't follow our rule. We said trigonometry applies to right angled triangles. So is there a way I can make this into a right angled triangle? And the answer is yes. Look, I can draw not like that, but like this, hopefully. I can draw a line down the middle, splitting that, and that can now be two 45-degree angles. If you can split any straight line perpendicular into to a point, then you can make it into two right angles, and that's exactly what we're looking for in this case. So we now have two right angles here. It's an equilateral triangle, so 60 degrees in each corner. We've now split this angle in half, so that will mean that these are both 30 degrees. So we know the angles in this triangle. We can choose to make these lengths whatever we want for this purpose, but we're going to say all the lengths are 2, remembering this one's split directly in half in the middle, so they're now 1. So what we now have is, from an equilateral triangle, we now have two right angled triangles that we can apply our trig ratios to. But first of all, we need to find out what is the length of this line here. We haven't defined this, so what is length? We're going to call this length A. And again, that's where we go back to our friend Pythagoras. So Pythagoras said a squared plus b squared equals c squared. And we can put our numbers in. So this side here, that's the longest side of the right angled triangle. So we know that that is c. And this side is therefore b. So we can say a squared plus 1 squared equals 2 squared. So a squared
plus 1 squared is 1. 2 squared, 2 times 2 is 4. So now we're here, and we can, so to get rid of this plus 1, we want to minus 1, but what we do to one side, we have to do to the other. So we'll minus 1 from that side as well, and we'll be left with a squared equals 3. So to get rid of the squared, we're now going to do the square root on both sides. So a is square root of 3. So we can now label that up. We now know that that's the square root of 3. So now we've got all the information of that triangle, and now we can look at applying trigonometry and finding out what the value of sine, cosine and tan is to each of the angles for these triangles. So firstly, let's start with sine. I'm going to apply it to this angle here. So I'm going to say sine 60. So remember, I've forgotten, what is sine? What is sine? Well, lest we forget, we can write SOHCAHTOA, and then we're never going to forget. So sine is opposite over hypotenuse. So if you want, you can write opposite over hypotenuse. Remembering that in an exam you would be wanting to show your working, so show the examiner you know exactly what you're doing at each step. And also to make sure you don't get confused with anything that you're writing down, you might want to go check it later. So in this case, what is the opposite of this angle? Looking directly across, it is this value here, root 3. And then the hypotenuse is the long side, and we know that that's 2. So root 2, root 3 over 2. So what we said there with sine 60, we found the ratio of the opposite side over hypotenuse. Now the opposite side was this side A, which we knew was root 3. We worked out it's root 3 from Pythagoras. So we found out the ratio of side A compared to the hypotenuse. And that's the opposite side when viewing it from this angle. Now, if we were to think about it from the other angle, so we now look at this 30-degree angle at the top of the triangle. What if we wanted to find out what the ratio of the same side A was compared to the hypotenuse, but using this angle? So think about it in a different direction. What information do we have here? We have the hypotenuse with the angle, and this side, this length for that angle makes up the angle, and it's the one next to the angle. So it's the adjacent. So now I've got the adjacent, I've got the hypotenuse, and I've got an angle. So I want to be using cos. So this time, if we were to say cos 30, and it's 30 because we're looking at it from this angle, we can say adjacent. We said adjacent is the root 3 that we've worked out, divided by hypotenuse, which is 2. So here we can now look at this triangle, say sine 60, opposite over hypotenuse, that's root 3 over 2. But we can also say cos 30 is root 3 over 2. So they're the same value because you're actually talking geometrically about the same length, therefore the same ratio. You're comparing the same length of the triangle, which is this side of the triangle here, in both cases. So it's labeled the opposite when you're looking at it from the 60-degree angle, but it's the adjacent when you're looking at it from the 30-degree angle. So they have to be the same value because they're the same length. Therefore, they're going to be the same ratio. So that's one thing to take away from this triangle. What about if we applied that in a different direction? Because we can consider it on the other length as well. So previously we were talking about the length in the center there. Let's now talk about this length here, the horizontal length at the bottom of the triangle. And again, you can look at that from both angles. So this time, if you were to look at it sine 30, and we're saying sine 30 because we're approaching it from this angle, and it is opposite over hypotenuse, which is going to equal opposite is 1, and the hypotenuse is still 2, hasn't changed, so it's a half. Now if we were to look at this same length here, this here, but view it from this angle, we're now looking at it and it's the adjacent length to the angle. So we're now going to be back using cos. The angle is 60 and it's adjacent, which is 1 over the hypotenuse, which is a half. So we've now applied trigonometry to both sides of that triangle and looked at it from both angles, and proved that sine and cos will give the same value if you're looking at the same length, because it's the ratio of the lengths compared to the hypotenuse, and that always holds true. So now let's finish off and look at tan. So if firstly we can look at tan 30. So we're looking at it from this angle. We've got opposite is 1. We've got adjacent, root 3. So we can say 1 over root 3. And for tan 60, we're now looking at from this angle. Opposite is root 3 and adjacent is 1. So there, which anything divided by 1 is just itself. So we can see that they're actually reciprocal when you look at it, because that's 1 over. So there we are. What I want you to take away from that triangle is that the ratios are fundamental in terms of they are showing the same geometry regardless of which angle you look at it from. And what you can understand from that is that you only need one of the angles in the triangle in addition to the right angle to be able to solve for either of those lengths if you know the hypotenuse. So now let's use trigonometry to solve some problems. So let's apply it to something, and hopefully you can see how that can be used in this context. So let's look at this triangle here. This might be something that you're presented in an exam, for example, and let's label it up. Let's call this A, B, C. This is your right angle. Let's give this angle 53 degrees, and they may give you one of the other lengths, or they would have to give you one of the other lengths to solve it. So let's say this is 14 centimeters, and the question is find length AB. Okay, so you can see straight away that what you know from right angle triangles is one way of finding a length is Pythagoras. So let's think. Pythagoras. Pythagoras is fairly simple maths, so can I solve it with Pythagoras? A squared equal A squared plus B squared equals C squared. Let's call this A, this B, this C. I've got A, but I don't know B and I don't know C. I've got two unknowns there, so I can't use it. So Pythagoras is going to be off the menu. So the next thing we're going to now have in our arsenal is trigonometry. So let's write so ca tour again, because we don't want to forget it. We don't want to be using the wrong thing. We don't want to be overthinking things and in the exam each time. So if you've got a note, write it down. So then how we're going to use that. So let's label up and let's think about what we've got here. So the long side, we always say that's the hypotenuse. That never changes. And we're now looking at this angle here, this 53 here. So we know this angle here is made up of the length of the hypotenuse and this line here. Therefore that's the adjacent to the angle, next to the angle. Directly across then is this side, which is opposite. So what we've got is we know opposite, and we want to find length AB, which which is the hypotenuse. So this is what we want to find. So we're not going to be using the adjacent, we're going to be using opposite and hypotenuse. So where's opposite? Here. Hypotenuse here. So we're going to use sine. So first, identify what you're going to use and then set it up. So we've got sine 53 equals opposite, which is 14, over hypotenuse. Okay, so we now want to solve for the hypotenuse. So let's get this off the bottom. So to get it off the bottom, we want to times by the hypotenuse. So we need to do that to the other side. So we now have, let's call the hypotenuse something. Let's call it C. So we're going to call that C instead. So we bring the C up. So we now have C sine 53. Now when it's written like this, remember I said it's not sine times 53 here, but when we use an algebraic term, we are actually saying C sine times 53. And that's going to now equal 14. So now we want to get rid of sine 53. To do that, we're going to divide both sides. So that leaves us with C equals 14 over sine 53. So now you can, this is a bit more complicated than we saw before where we had some nice terms to use, but you can put this into your calculator. So you can press sine 53 and then that'll give you an answer. Remembering to make sure that your calculator's on the degrees setting, not the radians setting, as that will give you a very different answer and something that we will talk about much later. And that'll give you an answer of about 17.53. Remembering your units here, we saw that was in centimeters, so make sure we want to be in centimeters. You might have a slightly different answer. Remembering, depending on the calculator, you might be able to store the full term that you get for sine 53, considering it has lots of decimal places. However, you might need to do sine 53 first, write it down to a good number of decimal places, and then use that onto your calculator. So you might get a slightly different answer due to rounding. And last step of any mathematical problem you're going to solve is, does it look right? Let's have a check back and see that that number makes sense in terms of the context of our problem here. So one thing we know about the triangle is the hypotenuse is always the longest side for a right angled triangle. So if this is 14 centimeters here, do we expect the hypotenuse to be longer than 14 centimeters? Yes, because it's the longest side. And that's at 53 degrees. So 17.53, that seems about right. It seems about right. So that's a plausible answer, as well as just having done it mathematically. That's not always going to mean you can look at something and say, yep, that's right. However, you can visually see if something's definitely not right. And I think for a visual check, that is pretty good. Let's move on to our next problem, and we're going to look at it slightly differently. We've talked a lot about using the angle and finding the lengths. Now let's look at it from the other way, because anytime we have a mathematical equation, we can, if we know some of the terms, we can find some of the others. So let's now look at how we can use trigonometry to find an angle. So we're going to do a pretty similar triangle, but remember, as long as it's a right angle triangle, doesn't matter the angles, these ratios and will always work. Okay, we're going to now look at this angle here, which we're going to label theta. So this time we don't know the angle. This is going to be 12 centimeters. This is 13 centimeters. And we're going to label this up as X, Y, Z. And this time we're going to calculate theta. Okay, so it's asking for what is the angle. And now the first thing to look at with this question is it says calculate theta. So what it's definitely not looking for you to do is to get your protractor out and measure the angle. So always take that away as first point. And then next is thinking about what we're going to apply, what's in our arsenal again. We know the trigonometric ratios, and we know that that gives a relationship between the angles in a right angle triangle and the lengths in a right angle triangle. So let's apply some trigonometry. So again, step one, let's think SOHCAHTOA. Easiest way, not forget or not do anything wrong, write it out. Let's label up what we've got. So what information do we have? So the longest side of the triangle, as always, we know that that's the hypotenuse. And then the others are in relation to the angle we're looking at. So this time we've got 12 centimeters here, and that is directly across from the angle. So that is opposite. Directly opposite the angle, so we know what that is. So what we do have is the opposite side and the hypotenuse. So again here we're going to be looking at using sine. We've got the opposite, we've got the hypotenuse, so we can apply sine. So let's just write out our ratio. Let's see what we have for sine. So we said for sine theta, that equaled opposite over hypotenuse. So let's plug in our numbers and think about what we've got now. So we say sine of, we're trying to find theta, so we don't have an angle, we don't have the number for it in degrees yet, that's what we're trying to find. And this time we've got 12 as the opposite side length over the hypotenuse, which is 13. So we now know sine of theta is 12 divided by 13, which if you put into your calculator, you can round that to 0.9231. Okay, so now we're very close. But what I said previously was that sine times the angle isn't what this term is saying. It's not sine times angle, it's a function. It's a function of a given angle. That's the angle is the input. So it's not as simple as saying 0.9231 divided by sine gives you the angle. You're not going to solve that in the same way. This time we're going to use the sine to the -1 button on your calculator, and that allows you to use the input here that you've calculated the ratio, and that's going to give you the corresponding value of the angle theta. So this time we can say sine -1 0.9231 equals angle theta. Therefore, angle theta equals 67.4 degrees. And that'll then be your answer. Now again, what we said was, let's look at it. Let's think about the geometry of that triangle. Does it look about right? So 67.4. Now remembering that a drawing in an exam isn't necessarily accurate, so you can't look at it and think, is that angle 67.4? But what you can think about is the lengths of the side. So if you've got 13 degrees and 12 degrees, you could do Pythagoras and work out what the other side is. So let's do that. Okay, so just quickly doing Pythagoras on this side here, B, we can show that this is 5. So what we know is that it goes up much higher vertically than it does along the bottom. So a more accurate picture of it would actually be like this. So if you were to now visualize it, you can look at that and think, yeah, that goes more than twice in the vertical direction compared to going along in the horizontal direction. Therefore, you would expect the angle to be beyond 2/3 of the way to 90, which it is, 67.4 degrees. Visually, that now looks about right. So we can say that it's probably correct in terms of a check that we've calculated it. So it should be right, but quick visual check is, yeah, we're pretty confident that that's definitely not wrong. So now we can use trigonometry to, with an angle, calculate the lengths of the sides of the triangle, and with some lengths, calculate the angle. But they're applied both to fairly standard just triangles. So what if you were presented with something which was a bit more of a physical problem? So you might get an exam, or in future, when you want to actually apply trigonometry, you're certainly going to be looking at how you can take a physical problem and represent it geometrically and then mathematically solve it. So this time you might be presented with someone saying there's a tree. So let's draw ourselves a nice tree here. A nice tall tree in a forest, and the question may say a tree casts a shadow 2.5 meters in length. If you drew a line straight from the top of the shadow to the top of the tree, if I could spell, to top of the tree, it would be at 60 degrees. How tall is the tree? Okay, so let's think about what information we've got here. And firstly, with any physical problem, see if you can do a quick sketch and try and understand what that written information is actually trying to tell you in terms of a problem. So it says the tree has a shadow. So let's say the shadow is here. So this is our shadow, obviously be a shadow of the full tree. So let's draw it as if it looks a bit like a shadow. So there's our shadow. Now it says here, the next line is, if you draw a line straight from the top of the shadow to the top of the tree, it would be at 60 degrees. So from the top of the tree here to the top of the shadow here, you can draw that there. That's at 60 degrees, it says. So let's get my pen back. That is at 60 degrees. And it says here, a tree casts a shadow which is 2.5 meters in length. So this shadow here is 2.5 meters. Okay, so now we can look at it as in a problem, and what we see is pretty much exactly what we were just seeing before. We've got a right angled triangle here with an angle with one side length. So we can draw that out. I mean, you can deal with it from there and do the maths. However, it is sometimes neater and quite much easier to just draw that out again, so you've just got the numbers that you're going to be dealing with. So we have 2.5 meters here. We have 60 degrees. And what we want to find is how tall is the tree. So this is what we want to find here. Let's call that T. T for tall, T for tree. Again, remembering in algebra, you'll use X, Y, Z's a lot. You might use A, B, C's, but you can really use most letters that you fancy. Okay, so let's think about what we're going to do. We're going to apply trigonometry again. So let's think about what we've got. Sarkar Toa. Step one, let's label up what we know and what we have. So we're looking at this angle here, the 60 degrees, and we've got one side here is the hypotenuse, but we're not interested in the hypotenuse this time. The other side that makes up that angle is the adjacent. And then looking across to the opposite side, we've got the opposite. So we're now armed with the information we need. We've got adjacent and opposite, so we are going to be using opposite, adjacent, so we're going to be using tan. So remembering that our ratio, tan, equals opposite over adjacent. If you do forget, you can just look back at SOHCAHTOA, forget which way around these are. It's opposite over adjacent, always in that order. So for the others, adjacent over hypotenuse for cos, and for sine, opposite over hypotenuse. So you can always go back to that if you forget. So tan of the angle is opposite over adjacent. So let's put our numbers in. So we've got tan 60 equals opposite, which is what we're trying to find. We're going to call that t. Now this is a bit confusing because we are using tan, but we're going to stick with it. 2.5. Now let's get the 2.5 off the bottom. So let's times by 2.5. You have to do the same to the other side. So that leaves us with tan 60, so 2.5 times tan 60 equals t. Now remember, we looked at the common triangles earlier and we actually worked out what tan 60 was. So there's two ways you can solve this. So the first might be, you might be in a non-calculator exam, for example, and you have to remember it. And so some of the special triangles and the common terms you can try and remember. You could draw out the half equilateral triangle that we talked about, or you could just remember it. So you could say, in that instance, it would be 2.5 times, and remember, tan 60 was root 3, and that's going to equal t. So therefore, t equals 4.33. And think about our units here. We've got meters, so 4.33 meters. But if it's in a calculator exam or you can't remember tan 60, remember that you can type in tan 60 into your calculator, and that should give you the value and should give you the same answer. So you can check that if you like. So we now know with triangles how we can use the angle to work out lengths. We can use lengths to work out angles. And lastly, we can look at some physical problems here, such as the tree scenario, and think about that question, put it into a simple geometric shape, and then that just boils down to the same trigonometry problems that we were just looking at with the triangles, and we can solve for them in the same way. Thanks for watching. Don't forget, I'll be making videos on a whole host of math subjects, so please don't miss anything. Please subscribe to the channel. And if you want to definitely not miss anything, press the bell icon and you'll never miss anything. Thank you very much for watching. This was Maths with Mitch, and I'll see you next time.